All right, so this lesson is going to start talking about Riemann's sums. It's going to dip our toe into the pool of integration. Although we're not going to talk about integration yet, we're laying the groundwork for that, okay? So let's take a look at the relationship between the graph of rate of change function and the area, the region between the derivative graph and the x-axis. So we're going to consider a tropical cyclone, Imelda, that brought more than 40 inches of rainfall over a 72-hour period in southeast Texas during September of 2019. So in order to avoid floodwater entering your home, you rent a pump that can remove water at a rate of 500 gallons per hour for the first 8 hours of pumping. As the storm grew stronger, you got a second pump. And for the next 16 hours, you could remove 900 gallons per hour using both pumps. Draw a graph that models the removal of the stormwater from your property. Label the axis correctly. Now, you already have this filled in on your notes, so we're just going to talk through it. So our x-axis is going to be our time. So that's t. And then this is going to be g of t, the y value, and that's just going to be gallons of stormwater in terms of time, which is in hours. And notice that we put units of measurement on there. So I know that for the first 8 hours, I can remove exactly 500 gallons per hour. And then after the 8 hours, I go and get another pump, and now I can remove up to 900 gallons of water for the next 16 hours. So that's going to take me to hour number 24. Okay, so when we say area under the curve, this represents the area between the graph and the horizontal axis. So find the area under the graph from 0 to 8. And what does this value represent in context of this tropical storm? Well, this is a rectangle. And so I know it's just length times width. So 500 times 8, which is 4,000. So the area under the curve is 4,000. What this means is, and the word that's underlined is the most important part, a total of 4,000 gallons of storm water was removed during the first 8 hours. A total of 4,000 gallons of storm water was removed during the first 8 hours. Find the total area under the graph for the entire 24-hour period. Explain the meaning of the context in the scenario. So now I've got this rectangle, which is 900 by 16. Multiply those, that gives me 14,400 gallons of water total. So to add those two numbers together from the first 8 hours and then the next 16 hours, that gives me the total of 18,400 gallons of storm water that was removed in the first 24 hours of the storm. All right. So we're going to use this concept and just take it a step farther. What approach can we take if the rate of change function is not constant? So in the tropical storm problem, those were very nice rectangles, and I can find the area very easily. But what if it's not a rectangle? What if it's defined by some curved function? The two big ideas in calculus are the tangent line problem and the area problem. In the tangent line problem, you saw how the limit process can be applied to find the slope of the tangent line. Think about the definition of the slope of the tangent line, i.e. the derivative at any point on the curve. A second classic problem in calculus is finding the area under the curve. It's bounded by a graph and the x-axis, and then any two x values. So in the tropical storm problem, it was between 0 and 24. Those were my two x values. A basic overview of area as limits. In the limit of rectangles approach, we take the area under the curve f of x from the interval a to b by approximating a collection of inscribed or circumscribed rectangles in such a way that the more rectangles used, the better the approximation. Finally, the number of rectangles is increased without limit, and bingo, we get the area, and that's integration. So specifically, it sounds very simple, doesn't it? Specifically, we're interested in finding the area of a region bounded by the x-axis and the graph of a non-negative function, meaning I'm trying to keep everything for now above the x-axis. This on some interval a to b. Note the requirement of f being non-negative means that no portion of this graph on the interval is below the x-axis. By using the rectangles, we can see that there are going to be 3 different ways of approximating the area for A, and these methods are known as Riemann Sum, and I will go over all 3 methods. All right, consider a 30-gallon aquarium being filled with water at a rate modeled by this function, which is definitely not constant. And I do want to point this out. Don't let those parentheses fool you. The of for sine does not end with pi over 8. It's sine of pi over 8t. I don't care for how they put those parentheses in there. So that is, you could even read that as pi t over 8 or pi over 8t, but both of those are in the of. Where t is time in minutes and r of t is gallons per minute. So r is already a rate. Find the volume of the water in the tank after 5 minutes by using 5 rectangles that are 1 minute wide and r of t in height. Okay, so they told me that I want to go 5 minutes. I'm going from 0 to 5. Let me change colors. From 0 to 5. They told me I could use 5 rectangles, which is nice. That means each unit gets its own rectangle. So here I go. I'm going, my first rectangle is going to be from 0 to 1. I go up to the curve, and then I come over and draw a rectangle. And then for the next rectangle, I go over to 2. I go up to the curve, hit the curve, then come straight over and draw rectangle number 2. And then for rectangle number 3, at 3, I go up to the curve, hit the curve, come straight over, and rectangle number 3. And then rectangle number 4. I know you guys see it, but I just want to do all 5 because the 5th one is a little different. All right, now, when I come over to 5, I come up and I hit the curve, and then I go straight over and straight down. Now, here's what I want you to notice. This is, well, you can't see that. Let's do purple. This is over. That's over. That's over. That's over. And that is under. So this is probably going to give me an over approximation of the area under the curve. Guys, the goal, I'm so out of highlights. And that's not going to show up. Let's go bright green. Nope, that's not going to show either. Ooh, more colors. Let's go, maybe pink will work. Maybe not. I need a bright color. Let's go dark purple. Nope. Okay. I want the area under the curve. So I want all of that area. So all of these pieces are not under the curve. But if I'm doing this with rectangles, it's kind of part of the deal. it's going to be over. Now, I do have a little underage right there that's going to help balance it out, but it's definitely going to be an over approximation. But that's what it is. It is an approximation, and I only have 5 rectangles. And I hope you guys can already start to see, if I went from 0 to 5, and instead of 5 rectangles, I used 50, that would be 10 rectangles in each unit. From 4 to 5, there'd be 10 different rectangles. Then my overs and my unders would get smaller and smaller and smaller. So the limit, as the number of rectangles goes to infinity, I'm going to get the exact area under the curve, because I'm going to have no overs and unders, or extremely microscopic overs and unders. Okay, so now I've got to deal with what I got. I got 5 rectangles. So I'm going to focus on the first rectangle. So his width is 1. So that's where this guy, oop, I don't want to do that. Let's fix that. He's a 1. There we go. So he's a 1, and he's a 1, and he's a 1. All these widths are 1 because all the widths of all 5 of my rectangles are 1. Now the height of these rectangles, and I have made a mess of these rectangles, so let's clean this up. There we go. So the height of the first rectangle is r of 1. The height of rectangle number 2 is r of 2. And the height of rectangle number 3, so you guys can see. So that's where these numbers are coming from. So let me take you to my calculator, where I have typed in y equals 6 sine of pi over 8x. I've made sure I'm in radians. I'm not going to the graph, I'm going to the table. So I'm going to go to the table. I make sure I started at 0 and go up by 1. And I can see that at 1, I'm at 2.296. If I wanted to go 4 decimal places. And then there's my 2 value. So r of 2 is going to be 4.242 or 243 if I wanted to round. And there's r of 3 and r of 4. And there's r of 5. So hopefully you can see where these numbers are coming from. And they are my y values, my heights at these particular numbers. Now notice I do not need an r of 0 because that is not a height of one of my rectangles. So then I just type all this into my calculator and I get this 23.625. So after 5 minutes, the aquarium has approximately 23.625 gallons in the tank, but I know from my illustration that this is going to be an overestimate, and it definitely is approximately. Now, give me a week or 2 with you, and I will have you guys finding the exact value of water in the aquarium after 5 minutes on a function like that, but not yet. By using more rectangles with smaller widths, we could achieve a better approximation. In fact, if we consider taking this to a limit of accumulating an infinite number of rectangles, we would arrive at the exact volume of water in the aquarium after 5 minutes. And this is called a definite integral, which is a couple lessons from now. And it's represented by the notation. Now check this out, because this is sort of your first introduction to what an integral looks like. So it's got this neat little curvy thing. And then I'm going from 0 to 5. This is what I'm integrating. And then you've got this dt on the end. And we'll examine all of that, but that's what an integral looks like. All right, so they talked about having 3 types of Riemann sums. And so for the aquarium problem, you could tell that all of those were going to be overestimates, except for the very last one. And so what we call this one that you just saw, this is called a right-handed Riemann sum, because, let me do some erasing, for this rectangle from here to here, I used, between the 0 and the 1, I used the 1 as the place to make the height for my rectangle. And from 0 to 2, I use the 2 to hit the function to make the height of my rectangle. Now watch what I could have done. If I had done a left-handed, and then between 0 and 1, I would take the left hand, 0, and 0 hits this function at 0. So that first rectangle would be flat. Then the second rectangle from 1 to 2 would go up to 1 and then come over and go down. And then from 2 to 3, on the left-hand side from 2 to 3, go up, hit the function, and then come down. And then from 3 to 4, it would go up on the left-hand side of 3 to 4. So that's why I'm choosing 3 and not 4, because it's a left-handed. Come over and make your rectangle. And then for the very last one, go up, hit the function, come straight over and down. So what you guys can see is this is going to be massively under, this is massively under, this one's massively under, this one's going to be under, but then this one's going to be over right there. So this is going to be an underestimate. And that's if it's a left hand. So right hand, left hand tells you, like if I'm looking at this pink rectangle, then do I want to use the 2 to determine my height or the 1 to determine my height? If it's the 2, then it's a right-handed Riemann sum, and if it's the 1, then it's a left-handed Riemann sum. And you just go up on either side, whichever one they tell you to, until you hit the function. And that's as high as that rectangle can go. And then it scoots straight over and then comes back down. So if I look at this very linear function, okay, so if I wanted to do a left endpoint rectangle for Riemann sum, then from here to here, I'm going to use the left hand where it hits the function. So again, that one's going to be flat. And then from here to here, I'm going to use the left, hit the function, straight over, come down. Then for this one, left hand, hit the function, straight over and come down. And then this one, left, hit the function, come over, come straight down. So that one's definitely going to be an underestimate. All right, and then for a right end, a right endpoint for a Riemann sum, so between A and B, I'm going to go on the right-hand side, go up, hit the function, straight over and come down. And then this one, right hand, so I'm going to go on the right-hand side, up till I hit the function, straight over, come down. Right hand, straight over, come down. Right, and this one's going to be an overestimate. Please do not think that a right hand estimate is always going to be an overestimate, because it's not true. It just depends on the function. All right, and then we have a midpoint. Now midpoint gets it a little bit better than a right hand and a left hand. Midpoint helps split the difference. So the midpoint says, okay, if I want to go from here to here, like if this is a 0 and this is a 1, then I'm going to go at 1/2. And I'm going to go up and I'm going to hit the function. And then I'm going to go straight over. And then between 1 and 2, well, I'm going to go at 1.5. And I'm going to go straight up and hit the function. And then I'm going to go straight over and down. And then between a 2 and a 3, I'm going to go at 2.5. I'm going straight up, hit the function, over, and down. And then between 3 and 4, I'm going to go at 3.5, hit the function, straight over, and down. So you can see for midpoint, it's got a little over and it's got a little under, and those really are going to help balance each other out. So this is a really good average. It is not exact, but it is a much better estimation than the right hand or the left hand. Okay, now I want to jump to the booklet that you have. It's a cute little booklet. It says Riemann Sum and the Trapezoidal rule, and it's got this cute little kit on it, and it should look like this. So if you'll grab that book and open it up. So here we've got Bernard Riemann, and he was in the 1800s. He was a German mathematician. He developed the method that can be used to estimate the area between a curve and the x-axis, and it uses rectangles to find the area because rectangles were something they were very familiar with and very comfortable with finding the area. If I only had the theorems, then I should find the proofs easily enough. So let's talk about Riemann sums being right versus left, and let's talk about something that is a curved function. So I have this cute function that's y equals x squared plus 3. So you know it's going to go up 3 and be a parabola. It opens up. And it's already got the values on here. Each bar is 1 tick mark. Okay, so the directions say use 4 left-handed rectangles to estimate the area between the curve and the x-axis over the interval 0 to 4. So 0, 1, 2, 3, 4. So I want the area. Here's what I want, guys. I want this area. I want to know how much that is. I want the area. And that's what integration is going to do. But before integration was discovered, old Riemann here said, all right, well, I'm going to estimate it with rectangles. And they're always going to tell you how many, and they're going to tell you which side. So 4, well, if I'm going from 0 to 4, then that spaces out really nice. It doesn't always do that. Left-handed. Okay, so for my rectangle from 0 to 1, if I want to be left-handed, then I'm going to go on the left hand, which would be a 0, and I'm going to go up. When I hit the function, that's where I stop, and I cut straight over and then drop it down. And that's my first rectangle. So he's under a little bit. All right, then between 1 and 2, left hand, so I'm at 1, I'm going to go up, hit the graph, and come straight over, and then drop it down. Okay, 2 to 3, left-handed, so I'm at 2. I'm going to go up, hit the graph, come straight over, and drop it down. And then for the last one, between 3 and 4, left-handed, so I'm at 3. Hit the function, straight over, and come down. So you guys can see that I'm leaving a bunch of area unaccounted for. So everything that's shaded orange is not going to be included in my area. So I come down here and I can say, will this estimate be an over or an under? Definitely under, because I did left-handed. And we're going to do the same thing in a second and go right-handed. Okay, so I need to find the area of these rectangles. Okay, so here we go. Area equals, well, the width of each one is 1. So here's what I'm going to do. Instead of length times width plus length times width plus length times width plus length times width, if I know that my width is the same for all of them, I'm just going to put a big one out front. Maybe that's too much. Maybe let's not do that yet. Let me show you each one individually and show you that they all have ones and show you how I can pull the one out. Okay, so here's the width of this one. So the question is, what is the height? Well, the height was determined by the left-hand side, which is a 0. So I could use the graph, but I could also just plug a 0 into my function, and I'm going to get a 3. So I know the height at 0 is 3. And then I'm going to add to it. And then the purple rectangle, I know his width is 1. And his height was based on the left-hand side, which is 1. So now if I plug a 1 in there, 1 squared is 1 plus 3 is 4. And then the blue rectangle, his width is 1. His height was determined by the 2. So now I'm going to plug a 2 in there. 2 squared is 4. 4 plus 3 is 7. And then from 3 to 4, that width is 1. And left-handed, so it's determined by the 3. So again, now I'm going to plug a 3 in there. And 3 squared is 9. And 9 plus 3 is 12. Okay, so here's what I was saying about one big 1 out front. Instead of writing all of these, I can just do 1 since all the widths are the same. And then just do all my heights. So it just simplifies it, and I know this one is very simple, but let's be honest, it's example number 1. Of course it's going to be simple. And these are going to get a little bit more intricate. So your widths are always is a strong word. Your widths are going to be the same most of the time, and if that's the case, then you can just pull the widths out and just add all the heights together. Because technically you're still doing length times width, length times width, length times width. And when you add all this up, you get 26 units squared because it is area. But again, that is an underestimate. So I would assume that the actual area would be a little bit more than that. Okay? So now we're going to do the same thing, but we're going to go right hand. So what I would love for you to do is pause the video and do a right-handed Riemann sum from 0 to 4 with 4 rectangles, doing it right-handed. And see how you do. And then when you're done, hit play. All right, so right-handed, 2, 3, 4. Gonna go up here, over, down, up, over, down, up, over, down. That's not a straight line. Okay, and then I can see that, heck yeah, this is definitely going to be an overestimate because all of this that is going to be counted in my area because it's part of my rectangle, but is not area under the curve. So I know that this is going to be an overestimate. I do know that the widths of all of my rectangles are 1. And now I just have to figure out my heights. And my heights are based on 1, 2, 3, and 4. Whereas before it was 0, 1, 2, and 3. So, and again, I'm just plugging into my function. So 1, that would be a 4. 2 squared would be a 7. 3 squared, 9. Be 12. 4 squared is 16. Plus 3 is 19. I got 42 units squared. So, doing a right-handed Riemann sum, I got an area of 42 units squared, and doing a left-handed Riemann sum, I got an area of 26 units squared. Therefore, I can conclude that the actual area is somewhere in between those two. All right, so now let's do a midpoint. And I know some of you are saying, well, if a midpoint is the best one, why don't we just jump to that? Well, because you need to be able to do a right-handed or a left-handed because in a multiple choice problem, they're going to tell you which one to do. Okay, so here I go. 1, 2, 3, 4, because I'm 4. Midpoint, 0 to 4. All right, but now my rectangles are going to be based on the midpoint y value. Oh, if I could only draw straight lines. So I got a little over and a little under there. Okay, so I'm going to go from here up, hit the function, over and down, over and down. Okay, midpoint up, hit the function, over, down, and down. And and orange. Midpoint. Over, down, over, down. Okay, so just to, really drive the point home, there's a little bit right there that's over, and he's over, but he's under, and he's under. So the red is the overages, and the pink are the underages that are not being counted. So in theory, now they are not exact, they're not equal, but they should cancel each other out and give us a more exact answer. Now, I'm looking for the area of these rectangles. Area is still length times width. Guys, the width of your rectangles is still 1. However, to get the heights, I'm not going to plug in a 0. I'm not going to plug in a 1. I have to plug in a 0.5, and then a 1.5, and a 2.5, and a 3.5. So I'm going to my handy-dandy calculator, clear that guy out, and I'm going to type in x squared plus 3. I'm going to go to my table. Feel free to pause this if you need to get caught up. I'm going to go to my table, but you know what? I need to start. I'm going to start at 0, but I need to go up by half. So I'm going to go to table set. I'm going to start at 0, and I'm going to go up by 0.5. And then go back to my table. And again, feel free to pause it so you can get caught up. So my 0.5 value is 3.25. My 1.5 value is 5.25. My 2.5 value is 9.25. And my 3.5 value is 15.25. So here I go. But again, the widths are all 1. So 3.25 plus 5.25 plus 9.25 plus 15.25, which is 33 units squared. Okay, now let's look. When we did a left-handed, we got 26 units squared. When we did a right-handed, we got 42 units squared. And when we did a midpoint, we got 33 units squared. So which one's the better estimate? 33. Is it exact? Absolutely not. But it's better than the right-handed and the left-handed. Okay. Now that was all super nice because we were going from 0 to 4 and we had 4 rectangles. Okay, so guys, same function, but now it says I want 8 left-handed from 0 to 4. Okay, so from 0 to 4, 8. That means the width is now half. Okay. Left-handed. All right, here I go. So between 0 and a half, left-handed. So I go up on the left-hand side, hit the function, come over, straight down. Then between a half and 1, left-hand side, go up, hit the function, straight over, and down. Okay. Between 1 and 1.5, left-handed, so go up, hit the function, come over, straight down. All right, keep on trucking. Oh, to be able to draw a straight line. Okay. there are my 8 beautiful left-handed rectangles. So let's see, I need my calculator to stay exactly where it is. I need half integer increments. And the first one I need, because we're left-handed, is from 0. So I need the 0, the half, the 1. I need to go all the way to 3.5. I do not need the y value at 4 because I don't have anything that goes up that high. So I am going to start with 0 again because I'm left-handed. So it starts with 0. So I'm going to do 3 plus 3.25 plus 4. And I'm going to go all the way to 3.5. Okay. Again, I have one big 1/2 out front because all the widths of all these triangles are a half. So I'm going to add all that up, and don't forget to times it by a half. And I got 28 units squared. And I know that that's going to be an underestimate because I can see from my graph that I have empty space underneath. Okay, so we've taken an interval of 4 and we've turned up the number of rectangles to 8. So now we're going to look at this guy. I've got a new function. And I'm going from -2 to 4. And I can't remember if yours is filled in or not. Regardless, I'm going from -2. So from here, 1, 2, 3, 4. So to here. And I want, okay, so this is odd. I want 3 left rectangles from -2 to 4. So to figure out how wide you're going to do, and a lot of you can already see that your width is going to be 2, but figure out the span of your interval. So I'm going to subtract those 2. So from 4 minus 2, so that's going to be 6, and I want to divide it by 3 rectangles. So I know that my width of my rectangles is going to be 2. So I'm going to here, and then I'm going to here, and then to here. So when I do the area, I'm going to put a big 2 out front. And I know that I want to be left-handed. So between the -2 and the 0, I want to use my left-handed y value, which is right here at 0. So that is a flat rectangle that has 0 area. And then from 0 to 2, I want to use my left-handed y value. Come straight over and down. And between 2 and 4, I'm going to use my left-handed y value straight over and down. So you guys can see I have a flat rectangle. I have this nice rectangle, and I have the purple rectangle. So I need the y values. Obviously, I know my first y value is 0. Then for my second y value, it sure looks to be 3. I'm just going to check it algebraically. It should be easy because I'm plugging in a 0. So if I plug in a 0 into this guy, yes, I'm going to be left with a 3. So his height is 3. And then for the last one, I'm plugging in, let's see, for the purple, I'm plugging in a 2 because that's my left-handed y value. So when I plug in a 2, 2 cubed is 8, so that goes to 1. 2 squared is 4 times a half would be -2 plus 3. So I got a 2. And if that just, makes you weird, uncomfortable doing the fractions and the powers, you can type that into your calculator if this was a calculator active problem, and go to your table. That would be fine. But I don't think that algebra was ridiculous. So let's see, 3 plus 2 is 5, and 5 times 2 is 10. So 10 units squared is the area. I would say this one's going to be an underestimate. I feel like we have more unders than we do overs. All right. Then this one says use 3 right rectangles to estimate the area. All right. So if I want 3, then my width is still going to be a 2. Okay. Come in here and erase. I'm going from here to here to here to here. And I want right. So feel free to pause this and do it on your own. Okay. So y values I need are 0 and 2 and 4. So 0 is the 3. 2 was the 2. And I need to find 4. If I plug 4 in here, 4 cubed is 64. An eighth of 64 is 8. If I plug a 4 in here, that's a 16. So it'd be minus 8. And then plus 3. So 3. That's a 5 plus 3 is 8 times 2 is 16 units squared. So I got a left hand of 10 and a right hand of 16. So now I'm going to do midpoint. So again, I challenge you to pause the video and go do this yourself. And if it's filled in on your notes, then make sure you know where those decimals are coming from. And I highly recommend you using your calculator if they're not going to turn out to be pretty. So midpoint, I'm going to come in here and do a -1 and a 1 and a 3. Now, I'm not dropping anything down there. I'm going up and going over. It's going to look like that. This one goes up, hits the graph, over, over. And then at 3, go up, hit the graph, over, over. So the values that I need to plug in are -1, 1, and 3. And those are not super nice. So I strongly recommend typing this into your y equals and using your table to find the values for -1, 1, and 3. The widths are still 2. And your y value should be 2.375, 2.625, and 1.875. Okay, so now we want to do 6, and we want to be left-handed. Okay, so I'm going to go back and erase everything. All right, so here's what I want you to do. I want you to pause it. We're going from -2 to 4, which is a width of 6. And now I want 6 rectangles. So my width now is 1. And which way do I want? I want left-handed. Okay, so again, pause the video. Try it yourself. There they are. Left-handed, so I need -2, -1, 0, 1, 2, and 3. I do not need 4's y value. So I'm going to go to my previous problems. I feel like I have all of these. Again, the width of my rectangles is a 1. 375, 3, 2.625, 275. Add all that together. There it is. All right. Okay, this is a great place to take a break. If you need to take a break, this is a good place to pause it, get up, go walk around, and come back, because we're about to change gears from rectangles to trapezoids. So another way to estimate area is using a trapezoid. So trapezoid has two separate bases that are two different widths. So you have base number 1 and base number 2. The height is the same throughout the trapezoid. So what we're going to do is we're going to take this trapezoid and we're going to turn it on its side so that this angle right here becomes flat, and this one is going to help follow the curve. And then this base, ooh, again, wish I could straight lines. There's your big base and there's your little base. Now you could also have one that does that, okay? The area of a trapezoid is 1/2 height, base 1 plus base 2. So base 1 is this height and base 2 is that height. Your height that was here is now the distance along the x-axis. So it's technically now your width, okay? So here we go. We have this great example of y equals 9 minus x squared. And I want to use 3 trapezoids to find the area on the interval from 0 to 3. So here's 0 and here's 3. And I want 3 trapezoids, which is very nice of them. All right, so here's what we're going to do. I'm going to draw heights that go up to the function. And then I'm going to connect with a linear line. Oh, that's supposed to be straight. Oh, to be able to draw a straight line. Okay, so do you guys see that this follows the curve so much better? I am going to be slightly under because this is concave down. So it does have that little bow action to it. So my straight lines are not going to capture all of the area, but oh my gosh, it's going to get so much closer than a right or left or a midpoint. Okay, so now we just have to figure out our area formula. So remember, area equals 1/2 height, base 1 plus base 2. Well, guys, this height right here is really the width of your trapezoids. And that's all 1 for this problem. So, and I'm going to have 3 separate trapezoids. So watch, I'm going to have 1/2, a width of 1, and then base 1 is this guy. So I need to know this function at 0. Well, that's 9. And then now I need this one, sorry, hold on. This one right here, which is this function at 1, which is going to be 8. So there is my first trapezoid. Plus 1/2 times 1, okay. So now I am here. Keep forgetting to hit highlight. I'm here. So this one is at 1, which I've already plugged in. That's an 8. And then this one right here is at 2. And if I plug a 2 in, that's 4. That'd be a 5. Plus 1/2 times 1. Okay, now I'm looking at this trapezoid. So the first one, this one right here, I already know is 5. And then this one right here, that height is going to be a 0. Okay. Now, let's be smart and let's look for patterns. I see that they each have a 1/2. I also see that they each have a 1. That will always be the case because they will always have a 1/2 because it's trapezoid, and their height, which again is the width, will always be the same because these are evenly spaced. So I hereby declare that we are going to do 1/2 and the 1 out front. So that way we don't have to write it 1,000 times, okay? Now, I want to look at this part. What do you notice? These trapezoids, from one trapezoid to a next, share a side. That 8 and that 8 are the same. That 5 and that 5 are the same. Now, what didn't get used twice is the 9 and the 0. The outer two edges don't get used twice. So here's what I'm going to do. I'm going to say, there's my outer edge, and then I need 2 times that inner edge and 2 times that inner edge, and then once of the outer edge, which is a 0. You're going to do so many of these, you're going to want a shortcut. So now I've got area equals 1/2, 9 plus 16 plus 10. So 1/2, 26, 35. So 35 over 2 units squared is the area. Okay, there's your trapezoid. Let's do another one. And let's practice that shortcut, okay? And see about memorizing our formula. Okay, so 3 trapezoids. I'm going from -4 to 2. Okay, hold on. From -4 to 2, that's a width of 6. I'm going 3 trapezoids, so each trapezoid has a width of 2. And I'm going from 1, 2, 3, 4 to 1, 2. Okay, now notice it doesn't hit 0. So, and I'm doing a width of 2. So -2 and 0 and 2 and -4. Okay, so here I go. I know that I'm going to start with a 1/2 and a width of 2 sitting out front of the whole shebang. All right, here I go. I'm going up. I'm taking him all the way up, taking that one all the way up, and taking this one up. And then I'm connecting that trapezoid. Now, this trapezoid looks like a rectangle because it is. This one. So we're going to be under here. Again, concave down. Trapezoid's going to be an underestimate. So let's see. I need this height at -4 once. I need the height at 2 once. But I need this height and this height twice because they're included in that trapezoid, and the 0 is in that trapezoid and that trapezoid. Okay, so here I go. I am going to plug -x² minus 2x plus 9 into my calculator, and I'm going to go to my table. So pause this, type that in so you can see those values. So at -4, it's at 1. And then I've got 2 times the value at -2, which is a 9. And then I've got 2 times the value at 0, which is 9. And then I only have one of the values at 2, which is 1. 1/2 times 2 is a 1. That's 18, 36, 37, 38. So 38 units squared. All right, so I hope this part is making sense. We've got some more trapezoids to do. Okay, so driving a shorter way, we've kind of already done that. So we're just going to keep plugging on as normal. This is all talking about adjusting the formula. But we're just going to keep practicing. In fact, no, this is a good one. Let's do this one. Okay. Here's my function. Tell you what, pause. Go type them into your y equals. Go ahead and pause and type them into your y equals. All right, I'm going from 0 to 2, and I want 4 traps. Okay, so from 0 to 2, and I want 4 trapezoids. So we are now on the half. And I'm going to go up and draw a trap, and up and draw a trap, up, trap, trap. Okay, so area equals 1/2. All right, what is my width? Well, the width, because I'm going from 0 to 2, my total width is 2, but I'm dividing it into 4 trapezoids, so I know my width is 1/2. All right, now I need the width at 0 one time, and that's a 0. I need the width at 1/2. Okay, so now go to your table. We'll go to your table set, start at 0, and go up by 1/2. Then go back to your table and get these values. But remember, at 1/2, I need that y value twice, because it is the right-hand side of the first trapezoid and the left-hand side of the second trapezoid. So that's going to be 2 times 2.625. And then the value at 1 is also going to be used twice. And I believe that's a 4. And then the value at 1.5, which is 3.375. And then the value at 1, which is 0. And 1/2 times 1/2 is a 1/4. Times all of that, which I think is, I don't know what that is. So whatever that decimal is, but I think your final answer is a very nice 5 units squared. So just make sure you're super comfortable with your calculator and your table and adjusting your table set. Okay, so then this just talks about how you can factor out a 1/2 and a 1/2 from each of the terms of the problem before. 1/2 because it came from the formula, the other 1/2 because that was my width. So we've talked about all of that. So moving right along. Now, what the AP exam loves to do is to ask you to find a Riemann sum using a table. So don't run out of steam on me yet. Stay super focused, because this is really important and you're going to see a lot of problems this way. And it's actually easier because you don't have to draw anything. All of your tables, it's like giving you the table in your calculator, but you have to know which values you need. So the National Weather Service kept track of the rate of snowfall for our most recent snowstorm. The snowstorm started at 9 a.m., which we will represent at t equals 0. So this is 9 a.m. The rate of snowfall was recorded every hour from 9 to 3 in centimeters per hour. Estimate the amount of snow on the ground at 3. So I need the area under the curve. The total amount of snowfall. How much did you accumulate? That is the area under the curve. So it says estimate the amount of snowfall by using 3 left rectangles. Okay. Well, guys, if I'm going from 0 to 6, so that's a span of 6, and I want 3 rectangles, then I know my width needs to be 2. So I'm here, here, and here. And I want left-handed rectangles, which means for this rectangle, that y value is important. For this purple rectangle, that y value is important. And for this red rectangle, that y value is important because I'm left-handed. So area equals width, which is 2 for all of them, and then I need my heights, 1, 1.4, and a 0.75. And when you type that in, you get 6.3 centimeters. Now remember, your answer is not a rate. Your answer is the amount of snow that has accumulated on the ground by 3 o'clock. And so that snow is going to be 6.3 centimeters, or that's what we're estimating it to be. Again, the area under the curve is the total amount that has accumulated. So now they want me to use 3 right-handed rectangles. Okay, that's fine. My width is still 2, but now I want to use the right-handed values. So that one, and that one, and that one for these 3 rectangles. So 1.4, 0.75, 0.25, and you get 4.8 centimeters. Okay, number 3 says, all right, 3, midpoint. Okay, well, my midpoint is here. Like my midpoint is sitting right here in this table. There it is. There's your midpoint. Now, your width is still 2. But your y values you're going to get from your midpoints of these rectangles. So that's going to be the 1.3, the 1.5, and the 0.5. And that gives me a total of 6.6 centimeters. And you can tell this one is over, and this one is under, and this one is just a little bit better. But I don't know if that one's over or under because I don't know the curve of this function. And that's one of the things you kind of sacrifice by using a table instead of a graph. Okay, number 4 says estimate the amount of snowfall by using 3 traps. Okay, so area equals 1/2, and then what is the width of all these trapezoids? And that is a 2. Okay, so now I'm going to use, let's see, different color. I'm going to use him once and him once, but I'm going to use that twice and that twice because those are interior sides of my trapezoid. So I have got, see if I can still see this. A 1 plus 2 times a 1.4 plus 2 times a 0.75 plus a 0.25. And again, feel free to pause this to make sure that you see where all these numbers are coming from and make notes off to the side if you have questions that you need to ask when we reconvene. This total gives me 5.55 centimeters. And the trap is going to be the most accurate. All right, now it says estimate the amount of snowfall by using 6 trapezoids. Okay, well, I need to go in here and clean this up. So let's go in here and erase. Okay, so 6 trapezoids. All right. So area equals 1/2. Okay, so what is my width? All right, let's look. So if I'm using 6, then my width is going to be 1 for each of them. Okay, now remember, I'm going to use the outside y values once and all interior y values twice. So I'm looking at my table. I'm going to use the 1 once, but then 2 times 1.3 plus 2 times 1.4 plus 2 times 1.5, 2 times 0.75, 2 times 0.5, and 2 times 0.25. Type all of that in ridiculously carefully. Don't forget the 1/2 and the one that's out front, and I get 6.075 centimeters. And that one squared. Well, not squared, because it starts talking about how much snow has fallen. That one's going to be the most accurate because it is trapezoid, which is great, and it's more trapezoids than any of the others. So for the trapezoids that we're using, 3 trapezoids aren't going to be as great because it has fewer trapezoids. If I did another Riemann sum that had 12 trapezoids, it would be even better. Okay? And then on the back of this booklet, you see this wonderful, just for fun coloring break. Feel free to color at your leisure. All right, so now we need to go back to where we left off before the booklet, which was right here. So go back into your notes. And we're going to talk about definite integral definition. So let f be continuous on the closed interval a to b, and let f be positive. Let a through a to b be partitioned into n subintervals of equal length. Delta x, that's your change in your x, is just going to be the big interval minus the little part of your interval and then divided by n. And that just helps you find your width, which we've done. Then the definite integral of f over a to b. And we'll skip all this part. But just look right here. It's the integral from a to b of f of x dx. And again, we'll focus more on the interval notation later. Right now, we're just worried about learning that the integration finds the area under the curve. So the general solution method for inscribed or circumscribed rectangles, so the lower the upper sums. Inscribed means it's all under the curve, and circumscribed means they're over the curve. Draw a rough graph. Use the formula. And this is length. I'm going to call it width. So this is how wide of a range are we going and how many rectangles are we dividing it by, and that tells you the width of each of your rectangles. Compute the x-coordinates of the rectangles at either the left end or the right end, and then compute the areas of each ones and then add them all together. If the graph is concave up, then a left-handed interval or a left-handed Riemann sum, think about it, if between these 2 points left-handed, between these 2 points left-handed. So that would definitely be an underestimate. If I was between these 2 points and I was right-handed, then it would be over. And then concave down is going to be, if I did this, then left-handed, again, would be under. But between these 2 points, if I was right-handed, it would be over. And we won't worry about the decreasing part. All right. So now the next page. There we go. So the next page, which is the very last page, so almost done, says Riemann's notes continued. And these are just some problems that I have found that I thought were really great. Very, very good multiple choice questions. So it says, let f be the function given by f of x equals 9 to the x. So we are exponential. We're going to do 4 subintervals, equal length. What is the value of a right Riemann sum for the approximation? And it tells me I'm going from 0 to 2 of f of x. And it told me what f of x is. So I've just got to know where to find all the information. I know that I want 4 intervals. I want to be a right-hand sum. And I'm going from 0 to 2. So if I'm going from 0 to 2 and I want 4 subintervals, so I'm going to do 2 minus 0 and divide it by 4. So I know that the width of my rectangles is a half. So I'm going to have 1/2 times. Now I want to be right-hand sums. Okay, so think about it without trying to draw this, because I don't want to have to draw the graph. If I'm at 0 and 1/2 and 1 and 1.5 and 2, those are all my x values. If I'm right-handed, then I want that y value, that one, and that one. I don't need the 0. So grab your calculator, type 9 to the x in, go to your table set, change your delta table to start at 0 and to go up by a half and go get the y values that go with those x values. And that should give you a 3, a 9, a 27, and an 81, which gives you a total area of 60 units squared. Make sure you're practicing this on your calculator. Don't just go along with the video. Make sure you're pausing and making sure you understand. All right, number 2 says left rectangular method, 4 subintervals going from 0 to 8. All right, now notice that. That says that f of x, I want the absolute value of, well, f of t. Now notice that the graph of f of t dips below the x-axis. So technically that would have negative area. I'm going to say that again. Because that graph dips below the x-axis, any area that's under the x-axis is going to be negative area. However, in the integration, it has set up the absolute value of f of t, therefore making it all positive. So if I want to go from 0 to 8, so I'm going to do 8 minus 0, and then divide it by 4 subintervals. So I know my width is 2. And so I know that I need 0, 2, 4, 6, and 8. And I want to be left-handed, so that means I want that y value, and that y value, and that one, and not 8's y value. So let's see. 0's y value is a 3. 2's y value is a 0. 4's y value is a negative 4, so I'm going to make that a positive 4. And 6's y value looks to be a negative 1, so I'm going to make that a positive 1. So 3, 4, 8 times 2 is 16 units squared. So what you're doing is you're finding all of this area and all of this area. This area would be positive. This area normally would be negative. So your answer would be negative here because you have more negative area than you do positive. But again, it's got that absolute value bars on it. Okay, number 3, estimate the area from 0 to 4 of square root of 25 minus x squared. And I just hope you guys remember that that's going to be a half circle with a radius of 5. I'm going from 0 to 4. So I'm looking for that area. Left-handed, 2 subintervals. So from 4 minus 0 and divide it by 2. So my widths are 2. Let's see, I'm going to be 0 and 2 and 4 are going to be my x values. I want to be left-handed, so I want the 0 and the 2. Yeah, 0 and the 2 and not the 4. So I'm going to plug in, this is easy enough. I'm going to plug a 0 into my x, and that's going to give me square root of 25, which is 5. And then plug a 2 into here, and that'd be 4, which would be the square root of 21. So 10 plus 2 root 21 is my area. All right, number 4, table below gives the velocity in miles per hour of a truck at selected time t in hours. Use a trapezoidal sum, 3 subintervals from 0 to 3. Okay, trapezoid. Area equals 1/2. All right, I need my width. Well, I'm going from 0 to 3. Okay, now this one is tricky because I'm going from 0 to 3 and I want 3 subintervals. So it's very easy to say, okay, all their widths are going to be 1. But check out the table. 3 subintervals indicated by the table. So I can't go 0, 1, 2, and 3. I have to use the t values that are given to me in the table. So my first width is 1/2. My second width is 1.5. And my third width is 1. So all my widths are not the same. So I can't pull the width out front. So I can pull the 1/2 out front. All right, so here it goes. So for my first trapezoid, my width is 1/2. And then my y values are a 20 and a 60. Plus, all right, my next trapezoid width is 1.5. And my y values are a 60 and a 40. And again, I'm using that 60 twice, but I can't do 2 times it because my widths are different, my 1/2 and my 1.5. And then my last width is a 1, and those heights are a 40 and a 30. And so let's see, 20 and 60 is 80. So half that'd be a 40. 60 and 40 is 100 times 1.5 would be 150. And 40 and 30 is 70. So 190 plus 70 is 260. And then I need to 1/2 that. So 130. So make sure that you're comfortable with a trapezoid in a table. And make sure you understand why I couldn't use the trick on this one to make it simpler, because all of my widths were not uniform. And that's one thing that they tend to do in a table to try to catch you off guard. Make sure you're paying attention to your details using the intervals indicated by the table. So just be careful there. All right, trapezoidal approximation for subintervals. I'm going from 0 to 3. Ugh. All right, so if I'm going from 0 to 3, so that's a width of 3, and I'm going to divide it by 4 subintervals, so my widths are 3/4. The nice thing is they're all the same. So trapezoid is going to have a 1/2 and then a 3/4 for my width. And then this is calculator active. So I'm typing e to the x into my calculator. And, okay, let's see. I need to go, I'm going to start at 0 because it tells me I'm going from 0 to 3. So I'm starting at 0 and I'm going to go up 3/4. So that would put me at 3/4. And then that would put me at 3/4 plus 3/4 is 6/4, which is 3/2. And then I'm adding 3/4 to that. 6/4 and 3/4, 9/4. And then 9/4 and 3/4 is 12/4, which is 3. I have to get all my x values. I know I'm starting at 0, and I know I'm heading to 3, and I know that I've got to be adding 3/4 to each one because I know my widths are 3/4. But I have to figure out what all my x values are. So now I need to go to my calculator and do y equals e to the x. And I need to go to my table, and I need to look up 0 and 3/4, which is 0.75, and 3/2, which is 1.5, and 9/4, which is 2 1/4, so 2.25, and 3. Now, because these are equally divided, then I can use the trick with, I need my 0 value once. I need 2 times the 3/4. Let me see. I don't have this written down. So let me e to the x, and I'm going to my table set, and I'm going to start at 0, and I'm going to go up by 3/4, so 0.75, and then I go to my table. All right, so my first one is a 1, and my second one is a 2.117. And then at 1.5, I'm 4.4817. And then at 2.25, I'm at 9.4877. And then at 3, I'm at 20.086. And again, make sure you're super clear on, I have 2s on the interior walls, but only 1 on the exterior walls, because it's trapezoid, and those exterior heights don't get used twice. So type all this in. Don't forget to multiply it by 3/4 and 1/2, and I get 19.97. Please make sure that you're typing that into your calculator to make sure that you're comfortable with that part of it. Don't understand the process, but be making some silly calculator mistake and not know it. All right, number 6, it says the table shows the speed of an object in feet per second at various times during a 12-second interval. Okay, various times, not necessarily equidistant. Estimate the distance using midpoint and 3 subintervals. So if I'm going from 0 to 12, so that's a width of 12, 3 subintervals. So my width should be 4, but I don't see a 0 to 4. 1, 2, 3, 4, 5, 6. So here I go. I've got to divide it up the way that they gave it to me. So I'm going to go from here to here. There's 1, 2, 3. There are my 3 subintervals. So my widths are not going to be the same, and I'm doing midpoint. So I'm actually going to be using these y values. So my width for the first one is 6, and my height is going to be a 14. My width for the second one is only a 2, and my height's going to be an 8. And my width for the third one's going to be a 4, and my height's going to be a 3. This is such a great problem because it's super simple and should take you less than 60 seconds, but it's making sure that you are reading super carefully. And when you type that in, you get 112. Okay, last one. Suppose the graph of f is both increasing and concave up. Increasing and concave up. So should look something like that. On the interval a to b, oh, dang it. Let's try that. There we go. From A to B. Then using the same number of subdivisions and with a left hand, a right hand, a midpoint, and a trapezoid, list them in order from smallest to greatest. Okay, so if I do left hand, let's do 2 or 3 subintervals. So if I do left hand, I'll do left in pink. So left. If I do left hand, then it's definitely going to be way under. Okay, I'm going to do right hand in red. Okay, so between this one and this one, I'm going to go up and use the right hand. So it's going to go over. So that's definitely over. So left is going to be down here, right's going to be up here. Now for midpoint. All right, so midpoint is going to be somewhere in here. So now I just need to know, is the trap going to be under or over the middle? So I'm going to try to clean this up a little bit so we can see it better. Okay, so for trap, here's B. Okay, so for trap, if you're concave up, if I have to connect this point to this point, the trap is going to go over it. If I made it more extreme, can you guys see it better? Do you guys see that if I connect those trapezoids, and oh, if I could draw a straight line, it's going to be above the curve. So the trap is going to be just over the midpoint. So it's going to be left and then midpoint and then trap and then right. Okay, so I hope that, I know that was a lot. It's a long lesson, but I feel like once you get the hang of it, these Riemann sums should be something that you're really comfortable with, and get excited when you see a problem because it's very concrete and very doable. It's also laying the groundwork for integration, which we start the next lesson. So get excited. Please make sure that you ask any questions that you may have, anything that didn't sit well at the beginning of the next class. Thanks.